Hello, good morning, everyone. I hope you had a wonderful Thanksgiving weekend and that you had some time to, rest a little bit and recoup from, all the work that you've been doing. So today we have very tough lesson ahead of us, and I will be doing it mostly on the whiteboard here. I'll be writing notes for you. The information overlaps with the PowerPoint slides. Um, so, after you write a note, you feel free to go over the PowerPoint slides as well to, have a second look at the material. That hopefully will help you understand it a little bit more. We do have a quiz scheduled for today, so please make sure you take some time to do that as well. Okay, so the quiz is available until the end of today, and it covers lecture 3 as well as lecture 4. So yeah, let's get started with our lesson. Get some paper. Um, and like I said, we'll be taking quite a bit of notes today. I think we also have a test coming up next week, if I'm not mistaken. Let me just quickly double check that for you. Um, you guys are 201. Yep, so the beetroot is done. Most of you did a fairly good job. Uh, Today is a metabolism. Yep, we will finish metabolism by Thursday. I will have a test 1 review for you next Tuesday, and then the test will be next Thursday. Okay, no class on the Thursday. The test uh, takes quite a bit of time. I do suggest you do it during our regular time slot, but as usual, it will be available from 6 a.m. all the way to 11:59 p.m. So more on that later. Just worry about the quiz for today first. All right, so lecture 5, right? Lecture 5, it is the last lecture that is covered on your first test. Now, by now, you should know metabolism refers to all the reactions that are happening in the body, right? And we talked about previously how there are 2 kinds of reactions. We have the anabolism and the catabolism. Catabolism involves breaking molecules down and in the process releasing energy, right? And then we capture those energy and we use it to build things that we need within the body. So today we'll be focusing on the main catabolic reaction that happens in the body, which, as you may recall, is cellular respiration. All right. The overall reaction equation for cellular respiration goes like this: glucose plus oxygen produces carbon dioxide plus water and energy in the form of ATP. Okay, we can, of course, write it as a chemical formula as well. So we have glucose plus 6O2. You probably learned about balancing equation at this point in chemistry, plus 6H2O and up to 36 ATP. For every glucose that your body breaks down, for every glucose that your body metabolizes, you can produce up to 36 ATP under ideal conditions. Do you always get 36? Probably not, but ideally, you would be able to get as many as 36. Now, cellular respiration is considered as a type of redox reaction, okay? A type of redox reaction. Let me just put it down here. A redox reaction involves the transfer of electron from one reactant to another. That's what a redox reaction is. One reactant will be losing electron, and then those electrons has to go somewhere, right? So another reactant will be picking them up. Right? So in this transfer of electron, in this process, we say it is a redox reaction. Okay? So what does redox mean? Well, the RE part, the re part, sorry, the red part, RED, that stands for reduction. Okay? Reduction means gaining electron. Okay, I'm just gonna write electron like that from now on. On the other hand, if something is oxidized, oxidation, that means it is losing electron. Okay. So loss of electron is oxidation. You can remember Leo. Gaining electron is reduction. You can remember Ger. All right. So in our reaction, in the cellular respiration, glucose is the one that is going to be losing electron. Okay? This is the one that is going to be oxidized. Okay, so we can write like this. It's gonna oxidize and become carbon dioxide. Okay, oxidize into carbon dioxide. So that means it's giving off electron, and those electrons are packed with energy. Right? We call them high energy electron, and ultimately they will end up on the oxygen. And when oxygen picks it up, it is going to be reduced into H2O. Okay. Now it's not a direct transfer. It's not like, you know, we take the electron off glucose and immediately put it onto oxygen. There are a bunch of steps that needs to happen in between, and that's what we will be learning about, you know, throughout the lesson. So I'm going to pause for a second for you guys to catch up with the writing, and also ask questions if there is anything that is confusing at this point. Does everybody understand what redox means and how it relates to cellular respiration? Yeah, we all good? Already. So can someone remind me, where does cellular respiration take place in a cell? Anybody? Where does it happen within the cell? You guys know this? I mean, it's on your quiz today, right? So you should know. That's right, Roy. Mitochondria is where it takes place. Okay, so let's write down cellular respiration. Even though the equation is just one equation here, okay? But it actually is divided into 4 main stages, okay? So I'm just going to write them out first, and then we'll go into more details later. So the first one is called glycolysis. Okay, glyco means sugar, lysis means to break. So in glycolysis, you're breaking the glucose into 2, actually. And then the second step is called pyruvate oxidation. All right. We know oxidation means losing electron, right? So this molecule will be releasing more electrons. And then we have the Krebs cycle and the electron transport chain, ETC. All right. So this is the cell, and this is the cytoplasm. And hopefully you will recognize this as the mitochondria, right? Okay, it's of course not to scale, this drawing. Okay, so this is mitochondria. You better know that, right? Like if I show you a picture of that on the quiz, you should know. So that's the mitochondria. Now glycolysis takes place in the cytoplasm. And you will take the glucose molecule, you literally rip it into 2 halves, 2 equal halves. I'll explain more later. Then they will go into the inside here, which is where number 2 and number 3 will take place. What's this location called? Anybody remember? What do we call the innermost part of the mitochondria? That's right. Okay, it says matrix. Excellent. And finally, we have number 4, which is the electron transport chain. And that takes place right here, right? In the cristae. All right, so we can write that down. This happens in the cytoplasm. This happens in the matrix. Matrix again, and then cristae. Okay? It's pretty straightforward so far, I hope. All right, moving on. Now I'm just gonna write the steps again. 1, 2, 3, and 4. Okay. So glycolysis, pyruvate oxidation, Krebs cycle, and the ETC. Okay, just short form here. I mean, you can write it all out again, but I just want to have a quick list here. So the first 3 steps of cellular respiration, it's all about ripping electrons from glucose. Remember, glucose is the reactant that is going to be oxidized. That's the one that is going to be releasing electrons. So what you want to do here is to remove the electrons from the glucose in the first 3 steps. Okay, so high energy electrons are released from the first 3 steps, from glycolysis, pyruvate oxidation, Krebs cycle. Now, if we don't capture these electrons, they will be lost. Okay, it will be wasted. We don't want to waste them. They have a lot of energy, so we must capture them. Okay, so I'm going to write down here, high energy electrons are captured by energy or electron, it doesn't matter, we will use them interchangeably, carriers called NAD plus and FAD. Okay, so these are energy carrier. They capture the electron, they hold it, and then they will transport them to the ETC. Okay, so let's take a look at this. A high energy electron, right? So I'm going to draw an electron. Okay. We will capture this with NAD plus. NAD plus. And once it happens, the NAD plus will become NADH. Now I'm skipping some of the technical stuff. Like some of you might be with like, where does the hydrogen comes from, right? Like it doesn't matter for us. Okay, so just know that the NAD plus is the empty form of the molecule. Once it picks up the electron, it becomes NADH. Okay, and then the NADH will take the electron to the ETC, okay, and then is gonna give up the electron, and then it will become NAD plus again. Yeah, it'll become NAD plus again. Hold on, let me move this out of the way. Okay, and then what happens to the NAD plus? Well, the NAD plus, here, let me draw this again. I'm sorry. It's gonna come back here, go here, and then the NAD plus will go back to the first three steps, and then it just keeps on cycling. Think of the NAD plus as a taxi, okay, and the electrons is the passenger. So the taxi is available right now, and then the electron gets on, the passenger gets on, then it becomes NADH. The sign lights up, it says occupied, okay? And then it will drive them all the way to the ETC, to the airport maybe, drop off the passenger, now is available for pick up more electron, right? More passengers. So it goes back to where the passengers are, the first three steps, then they'll pick up another one. And then it just keeps on going back and forth continuously. Does that make sense? Okay, but that's not the only option. Right? You can release electron, and I have another carrier. Instead of the MND plus, you can have FAD. And then the FAD is going to become FADH2. But same thing though. It's going to drive it all the way to the ETC. It will let the electron off, and it will be empty once again. And then it will be available to go back and pick up more electrons.
I have a quick question.
Please go ahead.
So why in the NADH is there no tube on FADH? There is a tube.
I
Because
know, right? So
H is
weird.
in
Yep.
Hofbrinkel, right?
No,
So
yeah. Don't do the Hofbrinkel thing. Yeah. Leave that in chemistry class. Yeah, this has not.
okay.
It has nothing to do with that. Don't worry about it. Has to do with the structure of NAD and FAD. But we're not going to go into it. But excellent question though. Yeah. Okay. Any other question? Are you sure? Okay, we pick up the electrons, right, from the first three steps. They hop onto these taxis. You can choose the NAD plus or you can choose the FAD, right? Two options, right? And then they drive you all the way to the ETC. You have to get off at the ETC, okay? Once you get off, those taxis are available to go back. Right? It's like a shuttling surface, where it just goes back and forth all day long between the first three steps and the fourth step. Think of the first three steps as like the hotel. And all these people want to go to the airport, hop onto the electron carrier, the taxi, drives you to the airport, the ETC, and you get off.
I have a question.
Yep.
So is the NAD and the FAD like relatively similar or
Yeah, they are very similar, but with one key difference, which I'll tell you right now. Okay.
uh,
So let's write this out. Right. What's the right word here, guys? Right, that I'm looking for. Help me out. So NAD plus and FAD pick up high energy electron and are blank into NADH and FADH2 respectively. Okay, what's the word I'm looking for in the blank? Is it oxidized or is it reduced? What's the right word?
so in the start they're gaining the electrons, so they would be reduced, and in the end they're oxidizing electrons because they're losing the electrons to give it back to the ETC.
That is correct, right? But in this particular context, right, NAD plus and FADH, they pick up the electron, as you said, right? And therefore are reduced, right? What color did I use for reduce? I think it was red, right? Yep. Okay. Doesn't really matter. I hope you're doing the color code as well. It helps you remember some of these words, right? And are reduced in the NADH and FADH2 respectively. Respectively just means like this corresponds to the first one and this corresponds to the second one, right? The electrons, let's finish this sentence, right? What medicine was saying. The electrons are then transported to ETC, where NADH and FADH2 are, electron gets off, right? Oxidized. Back into NAD plus and FAD. Make sense? And like I said, these two will go back to the first three steps. Just gotta quickly write here. Goes back to 1, 2, 3 to do what? Why are they going back to 1 to 3?
To start it again.
That's right. Goes back to 1, 2, 3 to capture more electron, right? The more electron they capture, the more energy we can produce, the more ATP we can produce. ATP is like money for cells. We want as much of them as possible, so that we can use it for various things, right? Lecture 4, I told you we can use ATP for things like mechanical movement. We can use it for transport. We can use it for enzymatic activity. Everything causes energy in the body. So it's good to make as many ATP molecules as possible. Okay. Now, hopefully you're still with me. And again, if you're not, that's totally fine. You just have to ask questions because I don't know what you don't know. Right? And if you have a question, someone else probably has the same question. And so please type it in the chat box, unmute and ask. What was I gonna say next? All right, so what's the difference, right? Someone was asking, right? Are NAD and FAD like similar? Yeah, they are pretty similar. They are both organic molecules. They have a bunch of rings in it, carbon rings. But there's one fundamental difference between them. Each NADH, this is the one that is already in the reduced form. It already has the electron captured. And each of them carries enough energy to make up to 3 ATP molecules. Okay? And each FADH2 carries enough energy to make 2 ATP molecules. All right. You might wonder why, right? Again, we're not going to go into the details. Just think of them as like different kind of batteries. Some battery holds more energy than others, right? You have your little circle ones that you put in your calculator. Those don't hold as much energy compared to the ones that is like in your phone, right? Or compared to the AA, AAA, 9 volts. Different kinds of battery holds different amount of energy. That's because of the way that they're designed, right? So similarly, because of the structure of NADH and FADH2, even though they both capture electrons, but one can hold more energy, right? NADH can produce up to 3 ATP, while the other one can only produce up to 2 ATP. All right.
I have a question.
Yeah.
So is the NADH faster than the FADH2 or?
Interesting way of phrasing it. It's not about faster or slow. It's not about speed. It's just
Okay.
about how much it's able to hold, how much energy is able to hold. Yeah,
Okay, so when they're going through the cycle, they leave and get there at the same time, pretty much.
exactly. Yeah.
Okay.
All right. I thought I had a poll question. Do I? Let me see where it is. Okay, here it is. Um, again, I'm not doing it in the same order as the PowerPoint slides. You can look at the slides later, okay? But here is a poll question that we can try right now. Okay, what do you think? You might need to take out your calculator. Okay, I only have 6 responses. That's a little bit underwhelming. I was really hoping you guys would get this. But let's talk about it. All right. This is the question, and it's really big. All right. This was paid. What slide is this? Slide number 32. All right. On the PowerPoint. Slide 32. In PowerPoint. Okay, this is a simple math question. Under ideal conditions, what is the maximum number of ATPs that can be produced? So for NADH, right? For NADH, according to myself, each NADH carries enough energy to make 3 ATP molecules. So how many ATP from the 4 NADH? What do I multiply by? 3, right? Okay, so 3 times 4 is 12 ATP. There are 3 FADH2, and this time we only multiply by 2, right? Which will give me 6 ATP. And if you add them up together, 12 plus 6, that gives you 18 ATP. Is that okay? Please ask if you are not sure about the math, because you will see this kind of question, you know, on the test.
So I have a question.
Mm-hmm.
And why for the last one, like you only multiplied by 2, not the 3 one? Like,
That's good. Yeah. So here, right, it says because FADH2 carries enough energy to only make 2 ATP, right? The NADH can make more, it holds more charges, more energy. FAD doesn't hold as much. Right? So the first one can make 3 ATP each, that's why I times it by 3. And then the FADH2 can only make 2. That's why I'm multiplying by 2. Okay, so these are rules to memorize basically, like how many each one can produce, and then you just multiply them accordingly. Does that answer your question, Shayna? Is that okay now? Yeah, all right. Shauna, I'm sorry, um, said it wrong the first time. All right, why don't we just try another one, right? Now I want you to just type the answer in the chat box, but don't press enter yet. Okay, we're gonna press enter at the same time, all right? Let's say we have 7 FADH2 this time. Okay, how many ATP? Just, type your answer in the chat box, and then I will say press enter, and then everybody will press enter at the same time. Okay. Oh, you guys already press enter. All right, let's see. Who else? Don't look at other people's answer. Try to figure it out yourself. No worries, it's all right. Don't worry about it. Okay, what is it? All right, if you have the answer, you can press enter now, if you haven't already. But hopefully, this is times 3. This is times 2, right? And then we will have 15 plus 14, which is 29 ATP. That's how you get the answer. Okay? All right, I hope that makes sense to you. Now we're gonna move on to the next concept. In cellular respiration, ATP molecules are produced in 2 ways. Okay, the name is very long. I will write out first and then I'll explain. One is called that first method is called substrate level phosphorylation. Substrate level phosphorylation. What does that even mean, right? So I'm just put a star here. To phosphorylate something means to add a phosphate to it. Okay, so that's what phosphorylation means. It just means you have to add a phosphate to the molecule. So substrate level phosphorylation goes like this. Okay. We need an enzyme. Everything needs an enzyme in the body. And we are going to have a donor molecule. Donor molecule. And this donor has a phosphate that is willing to give away. Okay. It doesn't mind. Yeah, take it. Take my phosphate, no problem. And what are we going to give the phosphate to? Well, in this case, we're going to give it to ADP. Okay, ADP. So in substrate level phosphorylation, an enzyme transfer a phosphate from a donor molecule onto ADP to generate ATP. Okay, like I mean, I'm not gonna draw another diagram, but basically it looks like this. Okay, the enzyme literally rips the phosphate off from the donor and pop it onto ADP. Of course, after ADP picks up the P, it becomes ATP, right? Adenosine triphosphate. Do you understand that? So this in this case, the enzyme is phosphorylating the ADP. It's putting a P onto ADP to make the ATP. I'll give you a moment to copy and ask questions if you have any. All right. Now, this is not a common method, okay? Only about, 10%, 10 to 11%, more like 11, but whatever, we just say 10. Approximately 10% of ATP are produced this way. Okay. Happens in step 1 and 3. Now, without looking back, try to visualize what number 1 and number 3 are. Right? See if you can recall that information. Okay. If not, look back. Right? See what number 1 and number 3 are called. So those are the places, those are the stages where we will be using substrate level phosphorylation to make ATP. Again, only about 10%, right? Of the 36 ATP that we are going to produce, only about 10% accounts for, it's produced using this method. Okay. So what's
this method, sorry.
No, go ahead.
So this method is a substrate levels phosphorylation.
That's right. That's the name of this method. Yeah.
Okay.
The other method is called oxidative phosphorylation. See, aren't you glad you're not like in person for the test? At least you don't have to spell that name. So in oxidative phosphorylation, this is substrate level phosphorylation. In oxidative phosphorylation, basically, the high energy electrons that were captured by NAD and FADH2 that are delivered to the last step, these high energy electrons drive the production of ATP. Right? So this is the main method of ATP production. Happens only in step number 4, the ETC. And exactly what happens is complicated. I will explain when we get there. Right now, we just, leave it be for the time being. Okay. So quick recap. We know cellular respiration is taking glucose, reacting with oxygen, producing carbon dioxide, water, and up to 36 ATP. This reaction is broken down into 4 stages, right? And they're written here: glycolysis, pyruvate oxidation, Krebs cycle, electron transport chain. It's not a one-step process, right? Each stage, there are multiple steps within. But the key thing to remember is that high energy electrons are released from the first 3 steps. These electrons needs to be captured. We can't let them escape. We will lose a lot of energy if they escape. So to catch them, we have electron carriers. The electron carriers are NAD plus and FAD. Once they pick up the electron, they are reduced into NADH or FADH2. They transport the electrons to the ETC, where they are oxidized back into the original form, so they can go back and get more electrons. Along the way, in step 1, 2, 3, we produce a little bit of ATP. Not a lot, a little bit, 10% of the total of 36 ATP. Okay, we'll make some using substrate level phosphorylation, where an enzyme will help us transfer a phosphate from a donor onto ADP. All those electrons that got off at the ETC, right? All these passengers, right? Keep on calling them, that got transported to the ETC, right? We can now use them to make a lot of ATP. Right? So that process of using these electrons to make a lot of ATP, that's called oxidative phosphorylation, OP. Right? And that only happens in step 4. Right? So just to tie it together one more time with the last part here, the NADH, right, carries the electron all the way to the ETC. And like I said, this electron will be used to make ATP using oxidative phosphorylation, right? So how many ATP can this electron make? This was from NADH. It got off from NADH. Now we're going to use it in oxidative phosphorylation to make how many ATP? 3 is correct. Well done. Okay. And then the electron that got off from FADH2, we're going to use it to make ATP now in oxidative phosphorylation, right? Only 2 this time. Okay. Still good. Not as good as the other stuff, but still has energy. All right. I hope we are all together up to this point. Right? That's like the hardest part, guys. Sort of. Okay. If you're okay up to this point, you should be proud of yourself. But seriously, any question before I move on? Nothing, eh? Okay. That's fine. That's fine. Let's go into more details for each of the the stages, the steps. Right, so let's do glycolysis. Now, glyco means sugar, right? It means glucose, really. Like sugar, but specifically we're talking about glucose here. Lysis, remember lysis? Right, lysis is the break, right? When you put an animal cell in a hypotonic solution, lysis, swell and break, burst. Right, so glycolysis involve splitting glucose into 2 pyruvate molecule. Okay. I want you to think about this. How many carbon do we have in a molecule of glucose? How many carbons? Please think about that. 6 is correct. 6 carbon. If you split it into half, 2 pyruvate molecules, that means each pyruvate has 3 carbons, right? Simple math there. Now, if you read this online, again, I don't think you need to read anything. I think the notes I'm giving you and then the lecture I'm teaching you right now should be enough. But if you want to read, that's fine. I just want to let you know, sometimes when you read online, it will say pyruvic acid. Okay, it's the same thing for us. Okay, I mean there is a difference, but we're not gonna care. Right? So pyruvic acid, same thing. All right, so it's gonna split the glucose into 2 pyruvate molecule. This takes place in the cytoplasm, right? Not yet in the mitochondria, just happens in the cytoplasm. And then glycolysis actually have 10 steps in it. Okay? There are 10 steps. Okay. And then separate it into 2 phases. Okay, I can hear some of you screaming. 10 phases, 10 steps. Are we gonna learn all 10 steps? Nope. Okay, you don't have to know any of the 10 steps. All right, but you do have to know that it's separated into 2 phases. Okay, so we have the energy investing phase. That's like step 1 to 5. Okay, and we have the energy yielding phase. Now, don't copy this next part. I just want to remind you about this graph here. Does this look familiar to any of you? Like, what is this graph showing? Specifically, like, what is this pink part here? Do you guys remember that from lecture 2, I think? No, not at all. Maybe. The peak, okay. Anyone else? Activation energy. There you go, Roy. That's great. What is that, though? What is the meaning of that? Right, this is the activation energy, right? What does it mean? The energy required for reaction to occur. Exactly, right? I hope that rings a bell for, for the rest of the class. Or some of you probably knew that, just didn't want to say it, but that's okay. So EA is the amount of energy required for reaction to occur. Right? So over here in glycolysis, glucose doesn't want to react. It's like, you know what? I don't want to do anything. I just want to, sit there and leave me be. Right? It doesn't have enough energy to go through with the reactions. Okay, and so what happens is, in the first 5 steps, we're gonna charge up the glucose. Okay, we're gonna pump it up with energy. We're gonna give it some energy so that it's willing to react. Okay, and that's kind of like the activation energy. You need to supply some energy before the reaction is going to take place. So in energy investing phase, okay, 2 ATP molecules. I'm just gonna say 2 ATPs. I don't know if it's proper to say ATP with an S. Doesn't matter. Okay, so 2 ATPs are used to energize glucose. Okay. Otherwise, it doesn't want to do anything. Right? It's like, we wake up in the morning. We may need some coffee. We need some breakfast so that we have the energy to get on with the rest of the day. Right? We need to charge up the glucose. We give it 2 ATP. Okay. Then in the energy yielding phase, we will produce 4 ATPs. Okay. Using, what's the method that we're going to use to produce ATP here? Are we using SLP, substrate level phosphorylation, or are we using OP, oxidative phosphorylation? What did we write earlier? What did we write down earlier? Right? Madison said OP. Anyone else? You guys, let's do a poll. Let's see if you're with me. All right. What do you think? How are these ATP produced? That's my question. Is it A, substrate level phosphorylation, or is it B, oxidative phosphorylation? If you're not sure, you can choose C. What's going on here? How are we producing the ATPs? Choose something, guys. I only have 6 answers. In case you missed the question, I am asking, in glycolysis, we will be producing 4 ATPs. Are these ATPs produced through SLP, substrate level phosphorylation, or is it oxidative phosphorylation? Or are you not sure? Come on, I need more answers so I know where you guys are at. Okay, so of the people who participated, 2 people said SLP, and then the rest says OP. I failed. I didn't teach you properly. The correct answer is SLP. Okay. How did you know that? Well, let's go back here and see. According to our notes, substrate level phosphorylation, where an enzyme transfer a phosphate from a donor molecule to an ADP, right? Only 10% of ATP are produced this way, happens in step 1 and 3. Okay, step 1 is glycolysis, right? Okay, so substrate level phosphorylation is the answer. Okay, the oxidative phosphorylation only happens in step number 4. All right, so for those of you who didn't answer, or for those of you who chose the wrong answer, I hope I have convinced you. Okay, so
I have a quick question.
Yep.
So the part about only 10%, I don't understand that. How are only 10% of it produced that way, if like in steps 1 and 3?
Okay, so yeah, so what's 10% of 36? Well, if you take 36 and then you times 0.1, right, you get 3.6, right? Okay, so that's what it means. That means of the 36 ATP, only 4 ATPs are produced using this method. Okay, so over here, I know it says we have 4 ATPs, right? But don't forget, we actually invested 2 ATPs, right? Okay, so that means How many ATP did you actually make in this case? Anyone can answer. Right? We invested, we paid 2 ATP to get the process going, and then you get 4 back. So in net, in a sense of like, subtracting your expenses, how many did you actually make? Right?
2.
Yeah, net 2 ATP, right? Okay. So that's what it means, right? You're gonna make 2 ATP here in step 1, and later you will see you make another 2 ATP in step 3. So that's 4 ATPs out of the 36, right? Which if you do the division, 4 divided by 36, it's 11%. So I round it down to roughly 10%. That's what it means. Does that answer your question, or did it make it more confusing?
I think it's okay.
Yeah?
Maybe
All right.
as we keep going.
Yeah, well, as we go on, hopefully it'll become more clear. All right, so energy yielding phase, we produce 4 ATPs. Okay, we also release some electrons. Okay, glucose releases some electrons. And anytime we release electrons, we can't let them go. We got to catch them. All right. So of course we catch them with NAD plus and generates 2 NADH. Okay. So that's what happens. In the energy yielding phase, we produce net 2 ATP. Right? We also produce some NADH. Now the NADH is not going to be converted into ATP immediately, right? Where do the NADH needs to go next? I have 2 NADH now. Where do they go? I think about it in your head. All right, what did I say earlier? If you're thinking about the ETC, that's correct. It will take it to the ETC, right? And then the electron will get off. Then you can use those electrons to make ATP, right? But that's a different method. That's oxidative phosphorylation. Okay? So let me show you this picture. You don't have to draw it, it's in the PowerPoint slides. Okay, but that is a summary of what happens in glycolysis. We start with the 6-carbon glucose. We invested 2 ATP. We charge it up. Okay, so that's called energy investment phase and energy investing phase. Then we will split the glucose. Okay, and here we're going to release some electron captured by NAD plus to becomes NADH. This goes to ETC. This one goes to ETC, right? And then we produce ATP, 2 ATP here by substrate level phosphorylation, And in the end, we get to pyruvic acid, or as I said, to pyruvate. For us, it's the same thing. 3 carbons. That's all in glycolysis. Okay. All right, I'm gonna do 2 more polls with you. Please participate, please. That's the only way for me to see if you guys are with me. All right. This one, you should get it right. I'll let you read it first, and then I'll launch the poll. And then we're gonna have a break after, okay? Go ahead, tell me what you think. Right. Anyone else? Why, where is the rest of the class? How come it's always the same 9 people? answer. I mean, I don't know if it's the same 9 people, but like it's always just 9 responses. Where are the rest of you? Oh my. Let's end the poll. Oh, we got one more. My pleat has okay, one more answer. 2, that's right. Net, right? Net means you have to subtract your expenses. Okay, remember we spent 2 ATPs in the energy investment phase, right? And then in the yielding phase, you make 4. 4 minus 2 gives you 2. All right. One more. Oh no, 2 more, 2 more. Okay. This one's also easy. Okay, let's go. How many carbon atoms are in each pyruvate molecule? If you have been paying attention, you should know this. You should know this. What is it? Anyone else? All right. Most of you got it right. Pyruvate is 3 carbons, right? Glucose has 6. You split it. 6 divided by 2 gives you 3. 3 carbons. This next one is quite complicated. I'll let you try first, and then I will explain. At the end of glycolysis, which of the following molecule has the most chemical energy? Okay, you really want to think about this one. Don't go with a gut feeling here. All right, I'm gonna leave it at that. Okay, so let's see. Glycolysis, right? We generate pyruvate, we generate NADH, we generate ATP. We didn't even generate carbon dioxide, so that's out of the question. All right, so ATP here, that's just one ATP molecule. NADH, as I told you, will go on to the ETC, and the electrons will be used to make ATP, right? Each NADH can make up to 3 ATP. I wrote it down for you earlier. So this is equivalent to 3 ATP, right? So already NADH has more chemical energy than 1 ATP molecule. That's not the answer, right? Okay. So between NADH and pyruvate, which one has more energy? Well, up to this point in cellular respiration, we've only generated 2 ATP, right? We've only generated 2 ATP. We can make up to 36 ATP in cellular respiration. So where are the rest of the ATPs? Where are the rest of the 34 ATPs, right? Well, that's basically locked in the pyruvate. As pyruvate go on to step 2, step 3, right? You will be able to harness more energy from it, right? So this can make many more ATP in step 2 and 3, right? And 4. So that's why this is the answer. Okay. So the PowerPoint slides, you can, the answer is C, okay? You can read through it yourself, right? It's basically everything that I wrote down for you. You know, but this is in PowerPoint form. The reason I did it on the note is because like I found that when I just go through the PowerPoints for something this complicated, you know, it just people just don't get it. And even if I write it out like this, right, I feel like some of you still not really catching it 100%, right? So you really still need to take the time to digest it, right? Watch the recordings. Okay, remember the test is next week, so it's important that you understand these things. All right, let's take a break. We'll come back at 9:41 and we shall do more. See you in a bit. Hello, welcome back. Let's continue with the next step. Okay, so next step, remember there are 4 steps, right? In cellular respiration, we just did glycolysis in before the break. So now we're gonna do pyruvate. Pyruvate oxidation. Okay. So the 2 pyruvate molecules generated in glycolysis, the last step, moves into, where does it go? Do you remember from the beginning of today's class? Where does pyruvate oxidation take place in? Where in the cell? Look at your notes, right? Find it. Okay, cytoplasm is where the glycolysis takes place. Cristae is where the last step occurs. That's right, matrix is correct. The 2 pyruvate molecules generated in glycolysis moves into the matrix of the mitochondria. Okay. Let me just go back here briefly to show you. Okay. Step 1 happens in cytoplasm, 2 and 3 matrix, and step 4 is cristae. So over here, the 2 pyruvate molecules generated in glycolysis moves into the matrix of the mitochondria. So 3 things happen here. Right? 3 things, 3 reactions happen to each pyruvate. So I'm just going to write it out for you like this. So this is pyruvate. And it has 3 carbons, right? We said that multiple times already. So first thing is we will remove a carbon dioxide. Okay. Step 2, we will release some electron. Well, that's why it's called oxidation, right? Pyruvate oxidation. We will remove more electron from it. Of course, those are going to be captured by NAD+, which then becomes NADH. I know I'm repeating myself a lot, but it's for your own good. I want to ask you one more time. Where will this NADH go? Hoping more of you would have the answer this time. Where is this NADH going to go? Right. To the ETC, right? Electron transport chain. Let the electron off there, make more ATP. Yeah. So now that we remove the carbon as carbon dioxide, it will only have 2 carbons left. Okay. But since we have carried out so many reactions already, right? The last time we charged the glucose was at the beginning of glycolysis, right? We supply some ATP, and then we did all these things to it. We made some we make 4 ATP, right? We make some NADH. Over here, we make more NADH. By now, the molecule is kind of running low in energy again. Like it doesn't want to react again, right? As the analogy I was telling you, right? Like we wake up in the morning, hopefully we had some breakfast, we feel energized, we're ready for the morning. But by noon, since we've done so many things, we're tired already. Okay, we need another meal. We need to have lunch. Right? So same situation here. The pyruvate, after going through all these things, it's lack of energy. So we need to give it a little boost, and that's why we're gonna add an energizing molecule called coenzyme A. All right, coenzyme A. And in the end, we're going to get something called acetyl-CoA. I'm really sorry. I know there's a lot of these weird words and it seems irrelevant. But like I said, I don't really dictate what you learn, right? It's it's the same everywhere you go for the pre-health program.
I have a quick question.
Yep.
So when it goes to the CO to the carbon dioxide and the NADH, is that like step 1 and then step 2?
Yeah.
Or how does it
Yeah,
go?
I'm gonna write it down for you right now. Good question. So
Okay.
step 1 is remove CO2. Okay, there's a fancy word for it in the notes, decarboxylation. Just think of it as removing carbon dioxide. That's step 1. Step number 2, right? We're gonna remove electrons from pyruvate. So we generate NADH. And number 3, we're gonna add coenzyme A. Okay, and again, if you missed what I said, the purpose of coenzyme A is to recharge the molecule, right? So that it will want to react in the next step. Okay, we extracted so much ATP, so many ATP, so many NADH from it already. It doesn't want to react anymore. So we give it a boost, right? We give it energy boost in the form of coenzyme A. Okay. So I want to reiterate to you that we started with glucose, 6 carbon. The glucose is split into, let me do that one more time, sorry. The glucose, which is 6 carbon, is split into 2 pyruvate, 3 carbons each, right? And each of the pyruvate will undergo these 3 steps in the matrix. Okay. So this is step number 3. This is step number 3. So in the end, by the end of pyruvate oxidation, we have 2 molecules of acetyl-CoA. Okay. Let me see if I have a summary slide here to show you. I don't think I do, but let's see. Oh, I do. What do you know? I mean, it's the same kind of information, but just more professional, I guess. There is your pyruvic acid, pyruvate. Same thing. Okay. Never mind the acetic acid here. Step 1, step 2, step 3. Done.
Sorry, so in the end you get 4 or 2 of the acid of the
Acetyl-CoA? Yeah, 2.
Yeah.
2 of them.
So okay, so from one process you get 2 of them.
Say that one more time. From one what?
From one process you get 2 of the acetyl enzyme.
From one pyruvate, you get 1 acetyl-CoA, right?
Okay, and then but then this glucose is 2 of them, or
That's right. So each glucose produces 2 pyruvate, right?
okay.
And each pyruvate will then become an acetyl-CoA. Right? So from one glucose, you get 2 acetyl-CoA in the end.
Okay.
Yeah.
Okay. Thank you.
Yeah. Now I hope you have the study guide with you. Okay, it's important that you print the study guide, like I said, at the beginning of the course. If you don't, I guess that's okay as well. You just have to make the chart in your notebook. I want to summarize everything we know so far. Okay. So stages in cellular respiration. You should be able to fill this in yourself, the 4 steps. Okay. I'll start the first one for you. Glycolysis. Okay. Oh, sorry, I keep on stepping on my shoelaces. I'm gonna tie it up. Hold on. Where does this happen? Again, please. Someone else tell me. Okay? Where does this happen? Glycolysis. Cytoplasm. That's right. Cytoplasm. Very good. Okay, so key products, right? Let's write it out. We have the glucose, and then we make 2 pyruvate. 2 pyruvate. 2 net ATP, right? And also 2 NADH. Right? Those are the key products. And I mentioned this already, but let's put a star here. These ATPs are produced by substrate level phosphorylation. Okay. All right. Number 2, second step. Let me just randomly pick on someone to answer. If you don't know the answer, you can say pass. First one in my list here is Kiana. Can you tell me what is the second step? Do you know? You can type it. You can unmute. What is the name of the second step?
Peruvian oxidation.
You got it. Very good. That's the one. Okay, so we're gonna put pyruvate oxidation. And where does that take place? Let's see. Aaliyah, do you know where that takes place? Aaliyah B. Okay, not available. Angel, do you know? Where does that take place?
I don't really know either.
Okay, that's all right. Gabriel, this is the third person on the list. Third one is a charm, right? Do you know? Thank you. The matrix. Very good. Matrix. Okay, and if you don't know where to find the answer, guys, it's right here in the earlier note. If you missed that, please watch the recording. It tells you where the steps happens. Okay. All right, key products here, key products. So we have 2 carbon dioxide, right? 2 carbon dioxide. That's the first step. You remove the carbon dioxide. Second step, we're gonna have 2 NADH. Right? We're gonna recharge the molecule a little bit by adding a coenzyme A, and in the end, we get 2 acetyl-CoA. That's just the way the names that they are called. Right? And I want to emphasize, like all these things, this is per glucose that we are talking about. That's everything we done so far. Any question, comments before I teach you number 3? I don't think we can go to step number 4 today. So maybe we'll finish with number 3. Nothing? Okay. So let's go back to our notes. We are already in the matrix, so these acetyl-CoA can just continue to react within the matrix. That's where the third step is going to be. They don't need to go to another place. So step number 3, Krebs cycle, which is also known as the citric acid cycle. All right. So I just want to show you this visually. Hopefully it makes sense to you. Let me see how we can do this. All right. Glucose, 6 carbon, right?
Quick question, sir. I know you may have already gone over it, but today the test will be posted. Quiz.
The quiz is already available. That's right. And it will
Yeah.
continue to be available until midnight.
Thank you.
Someone actually messaged me and asked if we are allowed to use notes. Yes, you can use notes for all my assessments. Okay, so sorry, I'm starting to lose my mind here. This is glycolysis, right? Okay. And then that's gonna, each of these things are gonna become acetyl-CoA, which is 2 carbons now. 2 carbons left from the original glucose. Okay. Why? Because, you know, carbon dioxide came out. Okay. So this is the second step, right? Pyruvate oxidation. Okay. Then we're gonna do Krebs cycle. Now, in the matrix, there is a 4 carbon molecule called oxaloacetate. Again, I'm really sorry with all these names. It was just already there. Right? So the first thing that happens is the oxaloacetate will combine with the acetyl-CoA. Okay, so 4 carbon plus 2 carbon gives you back the 6 carbon, right? 6 carbon. This is called citrate, okay, or citric acid. That's why it is also called the citric acid cycle. Okay, it's called a Krebs cycle, named after the person who supposedly, I don't know, discovered it or something. And then we have the citric acid because it's the first product of the reaction. And then many steps occurs in between. Okay, like many steps, too many that we don't really care about. Okay, but it's a cycle, so at the end you will regenerate the oxaloacetate. Okay, and then you will be able to combine with another acetyl-CoA. Now try to stay with me. The 4 plus the 2 gives you the 6. And then how do you think the 6 carbon will get back to 4 carbon? Where did the missing carbon go? Yeah, it loses 2 carbon, but where does it go? What molecule does it become? We actually saw this happen before. Right? When you lose carbon in cellular respiration, where do they go? Carbon dioxide, that's correct. Okay, so this is going to release 2 carbon dioxide. Okay, 2 carbon dioxide. Now, along the way, you will also release other things. You will release high energy electron. So that's going to create 3 NADH. It's going to create 1 FADH2. And you have to memorize some of these numbers, okay, to do some questions. And then 1 ATP. All right. So by the end of Krebs cycle, glucose is completely oxidized into carbon dioxide. Okay, let me write that down for you. By the end of Krebs cycle, glucose, which has 6 carbon, is completely broken down, oxidized, whatever you want to call it, broken down into CO2. Okay. Each cycle produces 1 ATP, again by substrate level phosphorylation, and 3 NADH, 3 NADH, and 1 FADH2. Remember, okay, I'll let you catch up first, and then I'll tell you what to remember. Okay, so remember, each glucose creates two pyruvate, which in turn creates 2 acetyl-CoA, which means 2 cycles happen for each glucose. Right? So that's why over here, I'll go back to let you copy in a bit. That's why over here, right, the other acetyl-CoA is going to undergo the exact same thing. The exact same thing. All right. So each cycle makes 3 NADH, 1 FADH2, and 1 ATP. But per glucose, you will have 6 NADH, 2 FADH2, and 2 ATP. Okay, so let's take a look at the carbon dioxide here. Right, remember the overall formula, right? Do you remember the overall formula? Right, C6H12O6 plus 6 oxygen produces 6 carbon dioxide, right? Let's take a look at where the 6 carbon dioxide came from. So we had carbon dioxide right here in the second step. Okay, that's 1 carbon dioxide, 2 carbon dioxide, 3, 4, 5, 6. Right? By the end of the Krebs cycle, glucose has been completely oxidized, completely broken down into carbon dioxide. Any questions?
Sir,
Mm-hmm.
like on the practice test that we have to label the cell for the animal and the plant cells, right? This won't be in the test, will it?
This won't. Yeah, no. The test is only the quiz. You mean, right? The quiz for
Yeah.
today. Yeah, it's only 3 and 4. Yeah.
Oh, so we don't have to label anything.
You don't have to label anything.
Like the animal cell or the plant cells?
Oh yeah, I might give you part of an animal cells and plant cells and ask you to
Mm.
label it. Yeah, I might give you a specific organelle and ask you to label it. Yes.
Okay, thanks.
Yep. All right, so let's go back to this chart. Over here, we have number 3, which is the Krebs cycle, right? Krebs, that's a person's name. And that also happens in the matrix. Now I'm talking about per glucose. Per glucose, we have 4 carbon dioxide, 2 ATP, 6 NADH, and 2 FADH2. I'm going to put a pink star here as well because these ATPs are also produced by substrate level phosphorylation. And I want to tell you again, that's the 6 carbon dioxide in total, accounting for the products, right? I haven't tell you where the water came from yet. We will next class. Yeah, that's pretty much it. All right. Let's take a look at this question. I'll let you guys finish copying first. What is the maximum number of ATP that can be produced with 5 turns of Krebs cycle? Okay. 5 turns. How many ATPs? Okay. You can type the answer, but don't press enter yet. I want everybody to have a chance to try. And if you're not sure, you can put not sure. So that way I know. Right? Give you about a minute or 2 to try this. Oh, okay. I see Hamon Yoon said 10. No, don't just count this ATP, right? Like you gotta count. Remember, all these things are gonna go on to step 4 and make more ATPs, right? So maximum number of ATP. You gotta take those into consideration as well. Right. Okay. George, you said 38. You know what? If you have the answer, just press enter. Right? We'll see. Roy says 60. Madison says 70. Homayun says 30. Anyone else? Take your time. Last call. Anyone else? Georgia changes her answer to 36. No, no one else? Uh-oh. Okay, let's take a look here. One cycle. One cycle means one spin, right? Let's take a look at our notes. One spin produces, the carbon dioxide doesn't matter. Carbon dioxide is the lowest of all in terms of energy. It doesn't make any ATP. So one spin, 3 NADH, 1 FADH2, and 1 ATP. I'm just going to write them down here. 3 NADH, 1 FADH2, 1 ATP. That's going to go on to step number 4. What number should I multiply this by? Yeah, thank you, Ramon. 3. 3 times 3 gives me 9 ATP. Right? And FADH2, I am going to multiply by 2, right? Less energy. 2 times 1 is 2 ATP. This one is already ATP, right? So we can just count it as is. Let's add them up. 9 plus 2 plus 1 is 12 ATP, right? Per cycle. One spin gives you 12. The question asks you for 5 turns. 12 times 5, 60 ATP. Okay, that's the answer. Okay, let's try another one. Okay, let's try 7 cycles, 7 turns. Okay. Go ahead, try it again. If you didn't get it the first time, see if you can get it this time. Okay, thank you. Anyone else? Yeah, so the key thing to know is one cycle, if you don't remember all these steps, then at least remember one cycle gives you 12 ATP, right? So 7 turns means 7 times 12, right? Let's keep it consistent. 12 times 12 ATP per cycle times 7 cycles, right? That is 84. All right. Okay, let's try one last one. 5. How many ATP does, I don't even know, sorry, my English grammar is not too good. How many ATPs do 5 glucose, can 5 glucose molecules produce in Krebs cycle? In Krebs cycle, yeah. What do you think now? Okay, I have 120, I have 60, and says 60 as well. Anyone else? $60 from Shayna. Roy says 120. Hey, I can make a multiple choice question from this with all the answers that are coming in. Okay, very good. Good job for trying. Let's think about this. 5 glucose, right? How many times do we spin? How many times do we turn for each glucose that we break down? 1 glucose spins how many times? Okay, we have some people say 1 time, some people say 2 times. Let's take a look. We started with 1 glucose. Each glucose get broken down into pyruvate, 2 pyruvates. Each pyruvate gets converted into acetyl-CoA, and each acetyl-CoA will spin once, right? So that means 1 glucose is 2 spins, right? 1 glucose equals 2 turns. Is that okay, Madison? You understand why it's 2 and not 1?
Yeah, because of both, it gets split to the 2 sides.
Yeah, you got it. Okay, so 2 turns, right? So that means if I have 5 glucose, right? 5 glucose. Glucose is, I don't know what's the right way to say this, but that's 10 turns, right? Okay. 1 turn is 12 ATP. 12 ATP per turn, per cycle, times 10 turns, 120. All right, so there will be some calculations in the on the test that you will have later on, but nothing more complicated than this. All right. I think we're gonna stop there. Next class, which is Thursday, we will finish lecture 5. And then, like I said, we will have a test 1 review next Tuesday. Your test 1 is next Thursday. Okay. No class next Thursday. You just have to do the test. Are you going to post? Yes, I will post the notes right after class along with the recordings. Okay. And that's it. Okay, thank you guys. Good luck with the quiz today, and I will see you on Thursday. Have a good one. Bye-bye now.
Have a good day.
You too.
See you, sir.
Bye-bye.